So this is the third session that we're having on large language models, and I'm going to talk about cultivating an AI-ready culture. I particularly want to address in-context learning and data retrieval using what we call RAGs, Retrieval Augmented Generation. We ended up looking at patterns in data and how neural nets can find those patterns. So given a data set, we can always generate a neural net model that, given some X, will produce the correct output Y, or a close approximation to that. So that's the magic of neural nets, is that they give us an ability to always be able to generate a model which approximates the data. Now, one particular kind of neural net is the autoencoder. And in this, we take an image. We don't need to label it because our goal is to reproduce that image. However, we're going to send it through a neural net where the layers have less and less nodes in them until we condense our data down to some minimum number of nodes. So all of these nodes, if you remember, we have input values. So these will be the pixels on the left-hand side. And then these will be individual numbers that we have for each node that will be resident there. So if I have three nodes, it's like an X, Y, and a Z. So you can imagine that this would specify some point in a three-dimensional space. Now, if we train this correctly, we can take those three numbers and expand them up again to the image. So this could be 1,000,000 nodes. And we do that by calculating the error between what actually comes out when we feed in this image and the original image that we want to match. So here we have, on the right, I've got the original image. On the left, this is what comes out of the decoder. But it turns out that overall, what's happening is that this neural net is learning the critical features of an image. So in this case, of a face. And it learns about things like the eyes and the nose and the mouth. And it turns out that these values in this latent space control features like the eyes or the lips. So by changing these values here, so for example, so there's the encoding part. Now let's just focus on the decoding. Now we have a space here that we have certain points in it that we've trained on, but now we can explore other points. And this will give rise to different faces that we've never trained on. So now we're generating faces potentially that have never existed in this world. And this is how we can, by controlling those points in that latent space, we can generate very different images. And so if one of those points, for example, controls the age, then by changing its value, we can get this succession of images being generated. So creating and understanding these latent spaces gives us this ability to generate things that have never existed. So here I'm showing this a two-dimensional space, and we may have 3 points that we've trained on, but now we can generate other points in that space and generate, what I'm showing here is faces. Now, here I'm showing what would happen. Let's suppose we trained on cylinders, and one of the axes was how high the cylinder is, and perhaps the other axis might be the width of it. So we train on the dark green, but we'd then be able to explore the space and generate cylinders that we didn't train on. These are the gray ones. So that's how we can generate things that we've never seen. Now, applying this to words, we can put words into a similar space, a kind of a latent space, but with words we call it an embedding space. So there's a whole theory of how we can train the weights in our neural net to generate this embedding space. But once we have the words in this embedding space, we can reason about what words are close or similar to other words. So here, for example, the vertical axis might be the gender of the person, and then on the right we have man being a king. It might be their job. So moving to the right, we'd have a different job for men and a different job for women, say. So what would happen is that these words would now exist in some kind of space, a vector space. So a vector is just a list of numbers. And the number of numbers that you have determines the number of dimensions of that space. So here I'm showing 3, 4, 5, 6, 7, a 7-dimensional space. Now, in reality, GPT-4 has these vectors are 12,000 long, so they're quite large, but we can represent them. Let's just stick to 2D here. So we can take words and represent them as a string of numbers. Here I'm just laying the numbers out horizontally instead of vertically. And we can do even more things with combining words together. So to be good, if I add each of these vectors together, I get another vector. And I could, for example, normalize that vector. That would just mean that it would be the same length. And we could then take a phrase and it would be represented by a single vector. Now we can extend this to documents. We can take a whole document and represent it as a vector. So here we've got documents, and we might chunk those documents, so every document might have 500 words, say, and then we'd have this representation of the document. And the representation the vector would represent, in some sense, the words in that document, would capture the kind of document, the topic that it was about. So if we had a query, what is a neural net? We could, in theory, find out what documents are close to this query. So they all exist in the same dimensional space, right? That they have the same number of numbers. And so we can compare them. So we'd embed our query, what is a neural net? That's this red vector. And then we'd look for the green vectors that were close to it, because they would be likely to contain information about neural nets. If they contained very different information, say about the eating habits of elephants, that we expect the vector to be very different to what is a neural net. So this technique is actually quite interesting. It's a fuzzy technique in the sense that we can pull back lots of documents that are close. So it's not just a single document, that we're getting information from around the area that we think is of interest. So what we do is we pull back the documents that we think are relevant, and we put the actual document, so not the vector, we put the actual document now into the prompt. So the prompt now contains the query and documents that are likely to answer that query. And we put that into our neural net and get a response that will answer the query. So RAGs can access documents, and the trick is to find what document has the answer. So the goal is to find what document. Now with structured data, we have SQL, but writing an SQL query is likened to spear phishing. It brings back specific data. It's not very good at bringing back data around the query that we have. And we've been through this before, but most data is coded, so it's difficult to understand. Typical data pipelines these days look something like this, where we have, and say, an online app that perhaps it's Amazon, and you click to buy something. That actual event comes through and is picked up. Here we're showing Google Analytics, which has got data about which web pages are being clicked on, etc. But the data is taken into the cloud. So here we're showing Databricks Delta Lake. And then we might transform that data. We might enrich it. We might manipulate it in ways that we can use, for example, to build machine learning models. And we've got near real-time pricing, for example, for Uber trips, where the customer here clicks on where you want to go. For example, you might want to go to Logan Airport, and in 2 or 3 seconds, you get back the price that Uber's going to charge you for that trip and what cars are nearby and how long you'll have to wait to get a car, etc. So we've got real-time or near real-time decision making in these pipelines. These are the stages that pipelines go through. This is pipeline maturity. So most companies are actually at the batch level. This would be, a SQL query, for example. But stage 2 would get you to near real time. And then you'd like to integrate your pipelines, and then you'd like to automate how data is processed, etc. And then even decentralize so that you have some resilience to failure and to potential attacks. Most companies are at stage 1 of maturity. How good are these RAG systems? Well, it depends. It depends on the quality of your documents. It depends on how you write your query, for example. But we'd like to be able to test these systems to see how accurate they are. And the problem that these RAGs solve really is that it grounds the LLM in the sense that we can tell the LLM to only make responses based on these documents. So there's less likelihood of hallucination. And you can even get citation of which document has been used to give the answer. So the issues are obviously the quality of the documents. For example, here you might have a blog post and you don't know if it's true or not. Admiral Nelson had his arm shot off in the Battle of Trafalgar. I'm not sure that's true. So document retrieval is still an art, and we'll go a little bit deeper into it in the next lecture. But certainly RAG systems are a great innovation, and they give you the means of extending or bringing up to date your LLM and giving it data that's relevant. PromptFlow is an Azure app that allows you to keep track of testing, for example, your RAG systems. This is showing how you can drag and drop and affect the workflow in ML Prompt. And here you've got evaluating the performance of a RAG system, the retrieval score, how good is it retrieving, groundedness, did it ground it in actual factual information, and then the relevance and the quality of the answer. So these are the ways that we test out RAG systems. And finally, we'll talk more about agentic computing. This is where we develop special agents that perhaps have access to a RAG system or data that they can leverage to make decisions. And we'll talk more about agentic computing later. So that's it for this lesson, and we'll get back to you to dig deeper into these RAG systems. Okay, bye for now.